Welcome to Geotechnical Engineering YouTube channel. This is Hector Levati. I'm going to present in this video concepts around stresses and strains from the point of view of the tensor analysis. So in order to start the explanation, I wanted to review a little bit very basic concepts around scalars, vectors, and tensors. So if we ask ourselves what is a scalar, so a scalar is basically a number that represents some physical property, for example, temperature, density, unit weight, all the ones you can read on the screen, because these quantities or these physical properties demand only a number and a unit. For example, temperatures demand a number, in this case 12, and the units degrees Celsius. A density, for example, in kilograms per cubic meters is 1,900, and so on. For example, time is another scalar magnitude that, for example, 10 seconds is just a number, a real number, and a units, and define the physical concept, the physical property of any material independently of the state being solid or fluid. So a scalar, at the end of the day, a scalar is a mathematical entity that defines certain physical concept or property with a real number and a unit. This is a way of defining a scalar, and we use a scalar on daily basis when we study engineering, civil engineering in particular. In here, for example, I have the results of an analysis made with finite element method in a soil that is considered isotropic linear elastic. So basically I have a scalar field. So a field is this map of colors that represent different values for this directional deformation in the Z deformation, which is the vertical deformation in this case. So every point of this map of colors in here represents a value of deformation. And it's a scalar field precisely because this map of colors is a function, is a scalar function, and every point is a scalar, so a value with an unit. In this case, for example, the unit is millimeters because we are talking about deformation. So this is the definition of the scalars and the scalars we use in the analysis in civil engineering, for example, and particularly in geotechnical engineering. So the next entity we are going to discuss is vectors. So what is a vector? So, for example, if we are talking about forces, displacements, velocities, we need more than a scalar to represent or to describe the property, because a force needs, apart from the magnitude, need a direction and a point of application, for example. The same thing for displacement, there's velocity, acceleration, tensions, or tensile or compressive forces, for example. So usually a vector is referred to a coordinate system that in this case is an orthogonal coordinate system, so x, y, and z. A vector can be represented by this arrow in red you can see on the screen, and the vector can be called P, for example, in this case, and P will be measured, it is to say the magnitude of the vector will be in kilonewtons, but this vector can be decomposed in the three-dimensional space in three components. Two of them will be horizontal and one of them will be vertical. The Z one will be vertical in this particular example. And so a vector is a mathematical entity that defines certain physical concepts or properties with three components in the three-dimensional space. And each component can be a scalar. For example, if we are talking about a concrete value for a vector. A vector can be, for example, the force applied to a sample in the lab. For example, this vector F in kilonewtons is the force we apply in a tensile test of a steel bar, and then this is the particular example of a vector expressed as a column matrix. So it's just this is just one way of defining this mathematical entity. Of course, mathematically, vectors, scalars, and tensor are defined analytically in other ways, but this is a more physical and more intuitive definition of the entity. In the same line, so talking in the same way, if we talk about tensors, a tensor could be, for example, the stress tensor, the strain tensor, permeability tensor, elasticity tensor, compliant tensors, and many others. So a tensor is, in the particular case of the stress tensor, is a quantity, is an entity, that is referred again to the orthogonal coordinate system x, y, and z, but it's referred to the state of stresses at a point of a soil mass, for example, if we are dealing in geotechnical engineering. So in there you have this cube, which is very small, is differential, it says, we say in mathematics, so it's as small as we need. And on this cube we have defined 3 components of axial stresses, sigma, x, y, and z, and we have 6 different components for the shear stresses. So we can represent this stress tensor with this cube, or we can represent as well using matrix algebra or matrices with this matrix where the main diagonals are the axial stresses and the rest of the elements are the shear stresses. So a second order tensor, and this is a second order tensor for mathematical reasons, is a mathematical entity that defines certain physical concept with 9 components in the 3-dimensional space. So in comparison to the vector, a vector in the 3-dimensional space, the vector we use in engineering, have 3 components. A tensor have 9 components in sets, and each component could be an scalar. So for example, an axial stress in one direction, x for example, y or z, or a shear stress in certain direction, x, y, y, z, or whatever is the whatever are the possibilities in terms of direction of the shear stresses. So once we have this mathematical entity that will allow us to define the state of stresses in the 3-dimensional space, we are ready to start discussing stresses and strain, because in the same way we have a stress tensor, we have a strain tensor. So we are going to start the study of the relationship between stresses and strains. So to start, we have in here on the screen basically the relationship between the stresses and strain for a ductile steel. So we have a sample of steel, a cylindrical sample of steel that is being pulled by this force F that we increase, and we record the deformations. So in this curve of stresses and strain, we can construct, we can sketch. We will differentiate several areas or several regimes. For example, in the first instance, we are going to load and we can unload to recover completely the deformations, and we have a linear deformation, relationship between the stresses and strain that is being made by this straight line from the origin of coordinate system sigma and epsilon with certain inclination. And this is what we know as the Hooke law. So if we are thinking about this one-dimensional example, it's easy to get this sort of information from the lab. So this first stage, where the relationships are proportional or are linear, we say that there is that the behavior is elastic, because when we release the loads, we are going to recover all the deformations, and is linear as well, because the relationship is proportional or linear. So from the point A to B, we are going to call the point A proportional limits, because from the point A, we are not going to have proportionality between stresses and strains anymore, so we are going to have a nonlinear behavior. So this curve represents the nonlinear behavior, because it's not straight anymore, until we reach the point B, which is the limit of elasticity. So this means that until the point B, if we unload the structure, in this case this steel bar, we are going to recover all the deformations, and we are going to have no plastic deformation or no permanent deformation. After the point B, we are going to plastify the material, we say, so the material will be behaving in a nonlinear way, but additionally, or behaving in a nonlinear way, we are going to have permanent deformation. So for example, let's say we unload the structure at the point C. So we are going to have an unloading a path like this, and we are going to have these permanent deformations in here, and some of the deformation will be recovered, so we will have some permanent deformation and some non-permanent deformation. Fortunately for us, in this presentation, we're going to focus only on the elastic regime, so we are not going to discuss plasticity. So we are in the regime, in the area, in the zone where all the deformations are recoverable. So our modeling of this material will be certainly simpler than if we go to study plastic behavior. So mathematically, if we want to represent this behavior, this linear behavior between stresses and strains, we are going to have this simple equation that is the Hooke law in one dimension. So the axial stress produced by the force F, which is equal to F over A, the area of the sample, is going to be equal to the Young modulus E multiplied by the strain, which is defined as the increment in length of the sample divided by the original length of the sample. This will give us this straight line in red, the relationship between the stresses and strains, and the slope, which is basically sigma over epsilon, is going to be the definition of the Young modulus. So the Young modulus is the slope of this straight line, and as you can see, because this is a linear elastic material, this means that the Young modulus is going to be constant, because the slope of a straight line is always the same. So this Young modulus will be a constant property, and we are not defining here any limits in the strength of this material, so we just have defined the relationship, the linear elastic relationship between the stresses and strains, and is elastic because we will recover all the deformation if we unload the sample. So the Young modulus E, again, is the ratio between the stresses and strain, and it's constant when the material is considered linear elastic. So these are the definition for this one-dimensional linear elastic material. Another thing that we can mention here is that in this case, because we are working in the unidimensional space, the stress, the strains, and the Young modulus are scalars. We are going to see that in three-dimensional applications, they are not scalars anymore. So if we have the case of nonlinear elasticity, so now we don't have a straight line as a relation between the stresses and strain, we have a nonlinear relation. So we have different slopes at different points, different tangents lines at different points of this curve. So this means that the Young modulus is not going to be constant anymore, and the relationship between the stresses and strain has to be represented by differentials. So now we are going to have the differential of the stress, sigma, the axial stress produced by F, is equal to a Young modulus that is variable multiplied by the differential of the strain. So the definition of the Young modulus in this case will be the variation of the Young modulus in terms of the deformation, or in terms of the strains. So this is the variation of the stresses in terms of the strains. So this is the definition of the Young modulus for nonlinear elastic materials in one dimension. Again, in this case, because we are still in the one-dimensional space, because this is an uniaxial stress test, tensile test, is basically sigma, the stress, epsilon, the strain, and the Young modulus are scalars. There is a little difference in here, because this is a scalar, but it's a scalar function. It's not a scalar anymore. It's not a number because it's not constant, but it's a function that is a scalar function, so it's a number that is changing depending on the amount of strain you have in your material. So the bigger the strain, you see at the beginning there is certain value for the tangent and the Young modulus, and the Young modulus will be in this case diminishing when you have more and more strain on the sample you are testing at the lab. When we go to the three-dimensional space, of course, the things become more complex, because we have 9 components for the stress tensor, as you remember. So this sigma in here will be the stress tensor now. So if the relationship between the stresses and strain remain linear in the three-dimensional space, we are going to have this stress tensor is equal to, and stress is called elastic tensor, multiplied by the strain tensor epsilon, that we are going to study in more details in a few minutes. And when you have a nonlinear relationship between stresses and strain, the stress tensor has to be represented by this differential of the stress tensor is equal to the stiffness matrix that or a stiffness tensor that will be variable in this case, because the relationship is nonlinear. It will depend on the degrees of strains, and the strain will be represented by a tensor again, which is actually the differential of that tensor, because the relationship is nonlinear. So there is a parallelism in here between the one dimension and two dimension. The only difference is that sigma and epsilon are second order tensors in this case, and actually E, the stiffness tensor, will be a fourth order tensor in this relationship. So the relationship will be more complex in terms of number of components, but we are going to see details about this in a minute. Finally, I wanted to mention that when we are dealing with geotechnical engineering, we usually need to run more complex tests than actual tests, because actually we don't test soils for tensile stresses unless we are doing some sort of research specifically for that matter. So in the case of soils, we produce a sample that is being tested in something called triaxial test, where we can apply forces in the horizontal and vertical direction, and we can apply pressure because this is a chamber that is filled up with water, for example, and we can apply pressure. So we are going to use other variables that are called the Cambridge variables, where usually use P as the mean stresses, actual stresses, and Q is the deviatoric stress we are going to define in a few minutes in this presentation. So before going forward to the details about the stress tensor and the strain tensor, I wanted to introduce the concept of soil failure, because we need to understand that we need to define, apart from the relationship between the stresses and strains, in which way the soil will fail. So the first question we can ask ourselves is: the soil fail by compression, tension, shear stresses, or what? And the reality is that the soil failure will be produced by a combination of the stresses. For example, if we try to think in a simple two-dimensional case where we apply forces, let's say this is the foundation of the building, or it's just a sample in the lab, if we increase the load, sooner or later we are going to plastify the soil, producing a line of failure that we can have in some cases this circular mechanism. So we are going to reach at some stage, when we increase the load, a maximum strength of the soil, and the failure mechanism we produce because we have reached the maximum combination of axial and shear stresses at some point of this failure line we have defined here. It's easier to see this mechanism when we have a slope stability problem. So we have a slope, we have this foundation here, we increase the load applied, and we are going to produce at some stage in this two-dimensional example a rotational mechanism that will make the soil fail in this way when we reach the maximum stresses at the points where we have defined the failure. In reality, naturally, these lines of failure can be not only circular, can be parabolic, logarithmic. So there are many examples with different types of mechanism of failure, but usually they are translational or rotational. So the concentration of the stresses at certain failure lines will be produced, and after that the failure, because you reach the strength of the soil. So this is the reason why you need to know two things when you are analyzing the failure: is the location of the failure lines where you have concentration of the stresses, and a detailed description of the state of the stresses in order to prevent or to know when the failure will be produced. And this is the reason why we need to know the stress tensor at every single point of the soil mass when we are dealing with the failure. And this is the reason why we are introducing here the concept of stress tensors and strain tensors. So in the three-dimensional space, then we have defined in here the stress tensor as this graphically this cube, differential cube with axial stresses sigma, x, y, and z, and these shear stresses that produce or form this matrix that can be another way of representing the stress tensor. And the first property we have to mention in here is that the stress tensor is symmetric. It's always symmetric because if it's not symmetric, rotations will be produced around axis X, Y, and Z, and we are going to lose the equilibrium. So this is called the Cauchy stress tensor. The Cauchy stress tensor is always symmetric. So if we rotate this element, this cubic element, or we rotate the coordinate system, we are going to see that the stresses change, because the stresses are quantities that depend on forces and areas and orientation of these areas. So it's logical to think that if we start, rotating this cube in this three-dimensional space, we are going to change the values of the axial stresses and shear stresses, refer to the same, for example, coordinate system X, Y, and Z. And sooner or later, we're going to reach a point. This is another property of the stress tensor, and actually it's a property of any tensor. So the stress tensor at some orientations reach a position where you have maximums, medium, and minimum axial stresses that are defined in here, that are called principal stresses, and for what the shear stresses are equal to 0. So this is the reason why you don't see any shear stress in these faces of this cube rotated at certain orientation. So there is always, for the stress tensor, a position where you find the principal stresses, sigma 1, sigma 2, and sigma 3. Sigma 1 is the maximum, sigma 2 is the medium, and sigma 3 is the minimum. Sometimes they are all the same, sometimes you have two of them equal and the other different, but you always can identify the maximum, the medium, and the minimum principal stress. Their directions that are always perpendicular one to each other, and on those faces where you have the principal stresses, the shear stresses are equal to 0. So in order to calculate these principal directions and these principal stresses, what we deal here is with the eigenvalue problem, basically. So in order to determine these principal stresses and principal directions, we need to resolve the problem of eigenvalues and eigenvectors. So in order to do that, we have to resolve the determinant of this expression in here. So the stress tensor sigma minus lambda, which is an scalar, multiplied by the identity tensor that you can see here in matrix form. So it's a tensor that have only ones in the main diagonal and zeros for the corresponding shear component, let's say. So at the end, after applying the matrix operation, you have the expression of the determinant in here. Not the determinant, is the matrix that you use to calculate the determinant. So from this expression of the determinant of this matrix, you can find this equation that is called characteristic equation. This characteristic equation is a cubic equation, then have 3 roots. So the 3 roots are the eigenvalues and correspond to the principal stresses. And the 3 eigenvectors of this matrix in here are the principal directions of the stress tensor in this case. And additionally to this concept of eigenvalues and eigenvectors that give us the values of the principal stresses and the direction of the principal stresses, there are 3 numbers that are called the invariants of the stress tensor in this case. So invariants of this tensor, and these are very important quantities because they are quantities that never change. So independently of the orientation of the cube that represent the stress tensor, and independently of the orientation of the axis we are using as a reference. So these are powerful numbers that we are going to use to study elasticity in other videos I will prepare. So the first invariant of the stress tensor is just the summation of the 3 elements in the diagonal, in the main diagonal. So it's equal to sigma x, y, and z, or sigma 1, sigma 2, and sigma 3. So this first invariant, as all the others invariant, never change. So independently of the orientation of the cube in the three-dimensional space, you can have these components or any other set of components, because there are infinite number of components in the infinite direction of the three-dimensional space. The summation of the main diagonal of the stress tensor as a matrix is always the same. The same thing happen with the second invariant, which is this expression in terms of x, y, and z, in terms of the principal stresses. And the third invariant is the determinant of the stress tensor, basically, which is have this expression for the coordinate system x, y, and z, and this expression when you have expressed the stress tensor in terms of the principal stresses. So it is the case that all the expressions in terms of the principal stresses are always simpler than the ones expressed in function of the general expression of the stress tensor. There is a very important property of tensors, and the second order tensors in general, and particularly for the stress tensor, that any stress tensor or any tensor can be decomposed in a spherical component and in a deviatoric component. So the spherical component of the stress tensor is shown in here, where you have a diagonal with the same value of the stresses for every component in the actual stresses, and the shear stresses are equal to 0, and the sigma m, which is the mean stress, is equal to a third of the first invariant of the stress tensor. So it's a third of the summation of the main diagonal of the stress tensor. So I'm making the operation in here, so the deviatoric stress tensor is going to be equal to the stress tensor minus the spherical component of the stress tensor. So this is the expression in matrix form. So in this case you have different values in general for all the components, the 9 components of the deviatoric stress tensor. Of course, because the deviatoric stress tensor is a tensor, it has its invariants as well, and the particularity that's happened is that the first invariant for the deviatoric stress tensor is equal to 0. You can check this making the summation of the elements in the main diagonal. There is an expression for the second invariant and the third invariant, same expression as for the stress tensor, because the deviatoric stress tensor is just a stress tensor as any other. In here you have an expression of the second invariant in function of this, the second invariant of the deviatoric stress tensor in function of the first and second invariant of the stress tensor, because it's an expression we are going to use to define the failure in the three-dimensional space in future videos. So there is another thing we need to discuss in here, is in the first place the definition of what is the pore water pressure. Pore water pressure as a tensor. So the pore water pressure is represented as a spherical tensor, as you can see, where the main diagonals are just the pore water pressure and the shear stresses are equal to 0, because as you know, in hydrostatics, you know that there are only axial stresses that are the same in every direction because it's a pressure, and this is what we call a spherical tensor, can be represented by PW, the value of the pore water pressure multiplied by the identity matrix I. This spheric pore water pressure, this spheric tensor, which is the pore water pressure stress tensor, can be helpful to define the effective stress. As you know, the effective stress is the total stress minus the pore water pressure in one dimension. So to generalize the concept of effective stress in the three-dimensional space, you have to do the stress tensor minus the spherical pore water pressure tensor. So doing that, you got this effective stress tensor, and you can express this in matrix form or in compact form, or using initial notation as well. And of course, the effective stress tensor is a tensor, so can be let's say decouple or decompose in the spherical component and the deviatoric component as well. So if you do this exercise, this mathematical exercise to decompose the effective stress tensor in the spherical component and deviatoric component, you arrive to the conclusion that the deviatoric component of the stress tensor is equal to the deviatoric component of the effective stress tensor. So the deviatoric component of these two tensors are the same. So they don't change. The only thing that changes is the spherical component. The spherical component of the stress tensor is not the same as the spherical component of the effective stress tensor. In this slide, we see the definition of the axial strain and the distortions in the three-dimensional space. So in this case, we are defining basically what is the right member of the relationship between the stresses and strains. So in the same way we have axial stresses, we are going to have axial strains, and in the same way we have shear stresses, we are going to have distortions in these directions, as you can see on the screen. So you will have epsilon x, y, and z, and define it as the derivative, partial derivative of the displacements in the directions u, v, and w that corresponds with the axis x, y, and z. And you are going to have distortions that are defined in this graph in here, distortions because you apply shear forces to the elements, the cubic element we have defined at the beginning of the presentation. And these are the mathematical expressions as partial derivatives in terms of the displacements in x, y, and z direction, and the derivatives in regard of x, y, and z, which are the coordinate system, the orthogonal coordinate system we have defined at the beginning to work with. So in the same way we have defined the stress tensor, we have a strain tensor. The strain tensor can be represented by the graph in here, these cubes that are being seen in 2 dimensions only from side view, or by this matrix where you have a main diagonal in red, epsilon x, y, and z are the axial strains, and the distortions are the gammas xy, gamma xz, etc., etc. And this strain tensor is symmetric in the same way as the stress tensor. So this is another property we can mention in terms of the strain tensor. The strain tensor can be decomposed as well in a volumetric component, or a spherical component and a deviatoric component. Here you have on the screen how they look like in matrix form, so the spherical strain tensor and the deviatoric strain tensor. And because they are tensors, you have as well invariant for the strain tensor in general, and you have invariant for the deviatoric strain tensor, and it happened the same in the stress tensor. So for the deviatoric strain tensor, the first invariant is equal to 0. And finally, I wanted to show you in here the definition of the volumetric deformation. So this is change in volume, reduction or increment in the volume of a portion of soil, and the octahedral shear deformation, which is related with the deviatoric component of this effect. So this is the distortion that volume of soil can experience, and are defined with this expression in here. So you have the volumetric deformation, the volumetric strain is equal to the summation of the elements in the diagonal of the strain tensor, so is equal to the first invariant of the strain tensor. And the octahedral shear deformation are defined with this expression in here in terms of the principal strains components, because in the same way that the stress tensor have principal stresses and directions, the strain tensor will have as well principal strains at some orientation in the three-dimensional space where the distortions are equal to 0. So this is the expression for the octahedral shear deformation.